All right, so picking up where we were last time, we were talking about polarity and how you predict the polarity of an overall molecule based on its Lewis structure and Vesper structure. So if we look at CH4, which is a tetrahedral molecule, it has four electronic groups, all of which are bonded. All the degrees are 109.5 degrees. And all of the electrons are traveling from the hydrogen to the carbon. And they're all going to cancel each other out. So they're all going in a similar direction towards the center, and they're all evenly spread out. So overall, they do not add together to make a net dipole moment. This molecule will be considered nonpolar. If we, however, look at NH3, which same thing, has four electronic groups, but now three of which are bonding, and one is a lone pair, these moments don't cancel each other out anymore. Plus, having that lone pair really helps make this molecule polar. And you can do the same thing for BF3 and CS2, and that BF3 and CS2 should also be nonpolar because there is no dipole moment for those molecules. All right, so what are the official definitions of these three different types of bonds? So if you have a polar bond, you were saying it is an unsymmetrical distribution of electrons, has poles. If we look at nonpolar, that is symmetrical distribution of electrons. There is no positive and negative end. And we also have an ionic bond, which is not a bond, that is complete transfer of electrons from one atom to another atom. And so nonpolar molecules, such as the CH4 we saw earlier, or the CO2, do not mix with polar molecules, such as water or NH3. And you know this already, you just didn't call it that, right? So nonpolar would be things like oil. Oil is a version of CH4. That's not going to mix with water. So these are two different types of polarities that don't mix with each other. Nonpolar things want to stick with nonpolar things. Polar things want to stick with other polar things. Ionic, however, will mix with polar. And to some extent, it can mix with nonpolar, but that's a fairly rare exception. And so how do we know what kind of bond it's going to be? It's really based on electronegativity differences. So if we have a difference of 0, we know for sure that's a truly covalent bond. If we have a difference of greater than 2, an electronegativity difference greater than 2, it is going to be an ionic bond. In other words, one atom has taken the electrons from the other. And if it's somewhere in between, it's going to be polar, a polar bond. And the increasing difference in electronegativity, as that increases, then we go from covalent to polar to ionic. The greater the difference, the more likely it is it's an ionic bond. So if we look at 3 examples of molecules that are made with different bonds, we can at least see what the molecule will look like in general. So if we have CSCl, this is 2 atoms. So we've done examples with more than 2 atoms, where if it has more than 2 atoms, you really have to build the whole structure and see the overall molecule. But if you look at CSCl, it has a difference of 3 minus 0.7, so the difference is 2.3, which, looking at our chart, is greater than 2, so this is going to be an ionic compound. If I look at this bit in SH, knowing what we know about this molecule, we would expect it to be polar, because it looks very similar to water, which we see this difference is it's 0.4, which means this is going to have polar bonds. And we see that these two polar bonds don't cancel out, and so this overall molecule is polar. If I look at this compound that has two nitrogens stuck to each other, well, there is zero difference in electronegativity. And so that is a pure covalent bond. And so we would expect that molecule this bond right here is purely covalent. They're evenly shared between those two nitrogens. But we would have to go through and determine the overall polarity of this molecule. And since it has lone pairs, it is most likely a polar molecule. It just has a purely covalent bond here in the center. But if we did this calculation of nitrogen to hydrogen, you would see that those bonds are definitely polar. Good, good, good. All right, so what we're going to do now is move on to the next chapter of material, which is chapter 5, which is Introduction to Gas Laws. So chapter 5. So chapter 5 is going to deal with gas laws and how they can help us determine what's going to go on in a reaction. So looking at what is gas and how do we measure how much gas we have? So pressure is a measurement we usually refer to when we're talking about gases. And pressure is really a measure of molecular collisions. So air contains gas molecules in constant motion. And being in constant motion, it means that they will be colliding with each other. So the result of these constant collisions between the atoms or the molecules. So the result of the collisions between themselves and with the container results in pressure. And so we measure pressure by looking at how much force is being exerted divided by how much area the pressure is being exerted over. And so force is mass times acceleration, which is this acceleration and mass are directly related to these collisions. And so if we think about what we know about pressure, we know that, right, pressure decreases with increasing altitude. So when you're up in the Himalayas, there is less air. And so if there is less air, then there must be less collisions. And if there's less collisions, there will be less pressure. Or if you have a sudden drop in pressure, the inside of your ear isn't able to equilibrate with the outside of your ear, which is when your ears pop. Because the inside of your ear has a given pressure, and if you go on a roller coaster or something and the outside pressure changes quickly, the popping is when you have the internal pressure and the external pressure trying to meet up again in the middle. So pressure decreases with increasing altitude because there are less air molecules. per volume, to be specific. So in reality, we deal with pressure a lot. We just don't always think about what is going on when we have these things happen to us. So how is pressure measured? There's a few different ways we can measure pressure. The first and most standard way is to measure atmospheric pressure. Now, atmospheric pressure is the average pressure at sea level. So atmospheric pressure is given the symbol ATM, and that is the average pressure of air at sea level. And so how we measure atmospheric pressure, if I have this set up, so this is mercury in the bottom of this. I have a bowl of mercury with a closed tube sitting in it, and as the pressure changes, it pushes down varying amounts on my pool of mercury, which then pushes the mercury on the inside of the tube up varying amounts. And so pure atmospheric pressure we consider to push the mercury up the tube 76 centimeters or 760 millimeters. And so 1 atmosphere is equal to 760 millimeters of mercury. We also use the unit torr, where 1 torr is equal to 1 millimeter of mercury. So if 1 millimeter is 1 torr and 760 is 1 atmosphere, then we can relate atmospheres to torr by saying 1 atmosphere is 760 torr. And we're going to interconvert between all of those units depending on what the situation is. All right, so now we know what pressure is, we know what units we should use along with it. So what are these gas laws that tell us about how gases work on Earth? So a sample of gas has 4 physical properties. They're all interrelated to each other. Pressure, that we just described, which is given the letter P. We also talk about volume, which is given the letter V. We talk about temperature. And then we talk about the number of moles. And so moles, right, is related to whatever the molecule is. The molecule has a molecular mass, and that molecular mass tells how many moles of a given substance it is. So all 3 of these are interrelated to each other through 3 small laws and then 1 bigger law that relates everything to each other. So let's look through the 3 small laws and then see how they're related to the overall ideal gas law. All right, so Boyle's law tells us about the relationship between pressure and volume at constant temperature and constant moles. All right, so looking at my picture here, I have 1 liter of volume at 1 atmosphere. And then my second picture, I now have half the volume I did. I was at 1, now I'm at half. Here the pressure was 1, but now the pressure is 2. So the volume has decreased by half, and the pressure has doubled, which tells us that they must be inversely related, right? This one decreases and that one's increasing, each by a factor of 2, which means that pressure is directly related to 1 over volume. So this little fish symbol means proportional to. So in this case, we can see that they are directly proportional, right? This decreased by half, that doubles. And so there must be some constant that relates these two to each other all the time. And so we don't know what that constant is, we just call it K. Where this is some proportionality constant. That'll be different for each problem you work. But this is useful because, right, I can rearrange this and say P1 equals K1 over V1. K is a constant, so that's true all the time. And if this was true, for example, 1 here, then I could say something about this over here, right? New pressure, new volume, same constant. So I could use two equations, rearrange these things, and say that P1 V1 is P2 V2, which equals K. And we don't care what K is. I just want to know if I know a pressure volume and I change either the pressure or the volume, I can now predict what's going to happen. So this Boyle's law states that as long as I'm at a constant temperature and constant number of moles, the pressure of the gas is inversely proportional to the volume. So as pressure increases, volume decreases. Or pressure decreases, volume increases, or vice versa. So let's look at an example of how that works. This may be true. Your lunch capacity may be constant, but that should be lung capacity. So let's say you're going to go scuba diving, which I won't because I'm petrified of the water. If you were going to go scuba diving, your lung capacity is a constant volume that you cannot change. So if you moved from the bottom of the ocean, which is measuring 3 atmospheres, to the surface, which is at 1 atmosphere, and you did it without breathing, what happens to the volume of air in your lungs? All right, so we want to use the equation, Boyle's law equation. So the initial pressure is where we are at the bottom of the ocean, 3 atmospheres. And your lungs, in general, hold, oh, that should be liters, sorry, liters, hold 3/4 of a liter, 0.75 liters. All right, we have now gone to the top of the ocean, and I want to know what the new volume of air that contains that is. So get out your calculators and figure out 3 times 0.75. 2.25 equals 1 ATM times V2. Divide both by 1 ATM. 2.25 liters is the new volume. So that's catastrophe, right? Because your lungs can only hold 0.75. They were full. And now they are 3 times too full, which is lung explosion, collapsed lung, instant death, something. Another reason not to go scuba diving. So you can see that the volume is much, much too much for your lung capacity if you choose to go scuba diving and just swim to the top without breathing. All right, so let's take a look at another law that tells us about how gases work. Charles's law. So this says that constant pressure and constant moles, volume decreases with decreasing temperature. So again, volume is proportional to temperature in some way. And if this is decreasing and this is decreasing, that means they are directly proportional. So I could say that is true. So as volume decreases, temperature decreases. That they are directly related in this way. Now, everything in this gas law chapter must use temperature in Kelvin. Because the units we're going to use for pressure and volume and moles all require that Kelvin be the temperature that we use. And so you may have seen this, you may have blown up a balloon in middle school, high school, and stuck it into a thing of ice water and the balloon shrinks, or maybe into liquid nitrogen and it shrinks, and then you warm it back up and the balloon gets bigger. The volume and temperature are directly related to each other. So this explains why hot air balloons work, right? Because you have a balloon that you have heated up the air inside the balloon more than the air around it. And so it's going to take up less space and actually float. The density is going to change, which is pretty neat. So the warm, less dense air can float above the rest of the air. All right, so let's look at an equation that uses Charles's law. So let's say you are given a balloon that has 3.2 liters, and you want to figure out what's going to happen when you submerge it into liquid nitrogen. So your balloon was at 3.2 liters. Submerged in liquid nitrogen, the volume shrinks down to 0.816 liters. We could figure out what is the temperature of the liquid nitrogen. So first thing, I gave you the temperature in degrees Celsius. Well, 25 degrees Celsius, you can get to Kelvin by saying 273 Kelvin plus degrees Celsius is our new temperature. Happens to be 25, so in this case, 298 Kelvin is our initial temperature. So using Charles's law, we can set up that proportion. Using our new volume, we try to figure out what this is. All right, so we have 3.2 divided by 298. Let's see, 1, 2, 3 sig figs, 1, 2, 3 sig figs, so 1, 2, 3 sig figs. All right, so we're going to multiply my question mark over here and divide over here. So my question mark equals 0.816 liters divided by 0.0107 liters per Kelvin. The liters cancel, and my final answer is 76.3 Kelvin, which you may not be as familiar with the Kelvin scale. So we may want, so let's convert it back to Fahrenheit, or to Celsius. That is negative 196 degrees Celsius. So cold, really, really, really cold. All right, good. Let's then take a look at the third law, called Avogadro's law. And as the name implies, this is going to have to do with the number of moles. So the relationship between volume and number of moles at constant temperature and pressure, think about blowing up a balloon. All right, so you start with the balloon being empty of air, and as you blow into it, you are adding moles of air. You're forcing them in, and the volume increases. So the number of moles increases and the volume increases, which means they must be directly proportional to each other. So it's going to look very similar to Charles's law that we just did, where V1 over N1 is V2 over N2. So as the volume of the balloon increases, the number of moles that are in there must have also increased. So looking at a practice problem, let's say I have a 3.86 liter container with 0.252 moles of gas. How many moles of the same gas would be required to fill an 8.5 liter container? All right, so we'll set up with the things that we know. 3.86 liters over 0.252 moles is proportional to some new number of moles. All right, so we have, let's see, 3.86 divided by 0.252. 3 sig figs, 15.4 liters per mole is equal to 8.50 liters, or some number of moles. Moving those around, liters cancel out, and I'm left with 8.5 divided by 15.4, 0.552 moles. And that makes sense, right? I have just about doubled the volume, so I would expect the number of moles to also double. So good. So those three laws make intuitive sense based on what we know in real life about gases. So now we're ready to combine those three laws together into what we call the ideal gas law. So the ideal gas law combines those three laws and covers all scenarios of a gas. So we have this PV portion from Boyle's law. We have the NP portion from Charles's. And then we have, VT from Charles's, and the NV from Avogadro's. And combine them all together, we get what we call the ideal gas law. Now the one thing that shows up in here that we haven't talked about is this R. R is the gas constant. And it's the reason we have to do everything in Kelvin. The gas constant, R, is equal to 8.21 times 10 to the negative second liters times atmospheres divided by Kelvin times moles. Which makes sense, right? Because this side of the equation has moles and temperature, so you want those to cancel out. And this side is in liter atmosphere, so you want those to cancel out. So R has to have the units of the things we are working with. All right, so let's go ahead and see how this ideal gas law works. All right, so looking at the ideal gas law, let's see if we can use it in this problem. So let's say I want to figure out the volume of 8.24 grams of carbon dioxide at STP. There's a few different things going on here. First, we have to figure out what STP is. And then I gave you the number in grams rather than moles. So we'll have to figure out how to get that from grams to moles. So first, STP is defined as 273.15 Kelvin, which is also 0 degrees Celsius, and 1 atmosphere. So STP, standard temperature and pressure, tells us that our temperature is known, and so is our pressure. So those two things are given. I'm looking for volume, and the last thing I need is moles. So I have to figure out how to convert this grams to moles. So we're going to start off with what is given to us. Grams of carbon dioxide. Then, in order to get out of grams into moles, we have to figure out what does this weigh. Well, carbon has a mass of 12, and oxygen has a mass of 16, and there's 2 of them. So it would be 32 plus 12, which gives us an overall mass of 44 grams per 1 mole of carbon dioxide. Sorry, 44.0 grams. So now the grams cancel out, and I'm left in moles. And I have 3 sig figs and 3 sig figs, so I can have 3 sig figs in my final answer. So now I have the temperature, the pressure, and the moles. So now I'm ready to plug this into my ideal gas law, which is PV equals nRT. So now I'm looking for volume, and I know the other things. So I'm going to go ahead and rearrange this and make it easier on myself. You could certainly plug it in and rearrange later. But I know the number of moles, 0.187 moles. And R is the gas constant, which is 8.21 times 10 to the negative second liter atmospheres over moles Kelvin, times the temperature, which is up here, 273.15 Kelvin, all divided by 1 atmosphere. So looking at our units, moles cancel out, and atmospheres cancel out, and Kelvin cancels out, and I'm left in liters, which is good, because I want to be in volume. So plugging that all in, I got 3 sig figs, 3 sig figs, 5. 1 atmosphere is exact, so that doesn't count. So my final answer is 4.19 liters. So that much carbon dioxide at 273.15 Kelvin, 1 atmosphere has a volume of 4.19 liters. Okay, good. All right, so now we're ready for a challenge problem. All right, so argon light bulbs have a pressure of 1.20 atmospheres and are found at a temperature of 18 degrees Celsius in this classroom. When they are turned on, they heat to a temperature of 85 degrees Celsius. What is the new pressure at this new temperature? All right, so we're going to think a little bit about how to solve this. So let's look at the ideal gas law again. PV equals nRT. All right, first question we need to ask ourselves is what is changing in this problem? So I had a temperature and a pressure and a new temperature, and I want to find the new pressure. Well, we don't have a law that does that directly. The ideal gas law is going to be the easiest. All right, so asking ourselves, right, pressure is the thing that's changing and temperature is the thing that's changing. Is the volume changing? No, right? We have constant light bulbs. Have I added or subtracted any moles to my light bulb? No, right? They're sealed, so there's no new moles going in or out of it. And R is the gas constant, which is constant. And so the N, the R, and the V are constant, which means I can plug it in and rearrange some things and figure out what to do with it. So what I'm going to do is I'm going to put everything that's constant on one side and everything that's changing on the other side. So pressure is changing and temperature is changing. So I'm going to say this. And then N, R over V. These guys are constant. Which means I can really say P1 T1 equals P2 T2, just like I did in Boyle's law. I had a fraction equal to a constant, which is now equal to a new fraction. So now I have a way of figuring out my new temperature at my new pressure. Let's go ahead and plug in what we have. 1.2 atmospheres over, oh, tricky, I gave it to you in Celsius. 18 degrees Celsius plus 273 is 291 Kelvin. And 85 degrees Celsius plus 273 is 358 Kelvin. So now we can plug those in. Or I guess P2. All right, so now we have 1.2 divided by 291 times 358. So I can have 3 significant figures, so P2 is now equal to 1.48 atmospheres. So we can use the ideal gas law in a bunch of different ways to solve for things we don't know. All All right, one more way that we can use the ideal gas law to figure out things going on with our gases is we can use the ideal gas law to determine how density works. All right, so it's known that 1 mole of ideal gas occupies 22.4 liters. And density, right, which is grams per milliliter, is directly proportional to its molar mass, right, which is grams per mole. So these two are directly related. The more moles, the more grams, the denser it is. So if I have density, which is measured in mass per volume, and I want to know about moles, which I call N, right? That's moles per molar mass. Oh, sorry, that should be grams. Just like I have it here. Sorry, it should be mass per molar mass. Yeah, grams per mole. So, I have PV equals nRT. But I just defined something new for N, where mass, right, is given an M, and molar mass is kind of given this weird scripty M, I guess, cursive M. So I can plug that in for N. All right, density is mass per volume. So now I have moles, but then I have this new thing where I have mass and volume, and I have a mass and I have a volume. So doing a little rearranging, moving the scripty M over to this side, and moving the volume over to this side, I now have mRT over V. But now, look, this guy is this. All right, and that guy was that. So now I have P, molar mass, equals, that's density, times the gas constant times temperature, which we can rearrange to get density by itself. And now I can determine the density of a gas knowing some things about it. It is proportional to pressure and molar mass, right, direct proportional, and inversely proportional to temperature. So as temperature changes, the density of the gas changes, which is what I said earlier, that as you heat gas up, it becomes less dense and starts to float. Or if you cool it off, it becomes more dense and sinks. So let's look at our last example for this lecture. Well, let's determine the molar mass and molecular formula of an unknown compound that contains iron and oxygen. Let's say the density is equal to 23.13 grams per liter at 375.5 Kelvin and 8.21 atmospheres. All right, so we want to use the equation we just developed on the previous page. D equals PM over RT. I'm plugging in things we have and then figuring out the molar mass. Since I want to know the molar mass, I'm going to go ahead and rearrange this so that molar mass is by itself. I'll multiply the RT times D and divide by P. And then I can plug in everything I know from the problem and figure out the molar mass. All right, so I got 3.13 grams per liter times the gas constant times the temperature, 375.5 Kelvin, all over 8.21 atmospheres. So if I look at things that cancel out, right, liters and liters, atmospheres and atmospheres, Kelvin and Kelvin, I'm left in grams per mole, which is what I want to be for molar mass. Let's see, how many simple figures? 4, 3, 4, 3. So I'll have 3 as my final answer. 23.13 times 8.21 times 10 to the second times 375.5 divided by 8.21. Let's see, 86.89 grams per mole. Yeah. All right. So that is M. Now the molecular formula of an unknown compound is going to be related to, right, this is the molar mass. So if I am looking at your periodic table, let's see if I can find your periodic table. I think I have one over here. Here we go. Iron has a molar mass by itself of 55.85. And oxygen has a molar mass of 16. So if I had one F and one O together, 55.85 plus 16, I had FeO. That would have a molar mass of 71.85 grams per mole. I could double the iron, but that would put me way past 86. So let's look at what happens if I double the oxygen. 55.85 plus 16 plus 16. That is 87.8 grams per mole. So this must be the right molecular formula. All right, I'm going to stop there. We'll pick up chapter 5 when I get back a week from today, and we'll talk about more gas law stuff and talk about the kinetic molecular theory of gases, how we know gases behave the way that they do. All right, have a good week.